Okay, let's start. Today we will go over, actually finish up the material for today for the course, almost. We will go over section 8.6, 9.3, 9.4, 9.2, 4 sections. Then next week is your test. Your test 4 will cover chapter 7 to chapter 9. Okay, and after the test next week, I will teach you a little bit more, but it's more about calculator skill. Now, it seems like we cover 4 sections today, and that's a lot, but actually no, because we already have the framework that we get from hypothesis testing that we learned last week. Okay, now you will see that what we do here from now on is just modification to those 6 steps that we have. And most of the time, the modification will be on step 2, 3, 4. Okay, like for example, on this hypothesis testing on population variance or population standard deviation. First modification on the test statistic, on the hypothesis, the null hypothesis and alternate hypothesis, therefore, will be on sigma squared or on sigma, depends on the wording of your step 1. Okay, but you will see, even though the test is on population standard deviation, in our step 3 and 4, we are actually testing the corresponding population variance. Okay, now, and in step 3, the test statistic is given by this. This is the modification from what we learned last week on the the confidence interval thingy. Notice that in confidence interval, our sigma squared is bounded above and below by n minus 1 s squared over chi squared right, and the one on the right hand side is divided by chi squared left. Right? Do you remember that? Now, basically, what happened is you switch the position of these two. Switch the position of these two. Okay. Yeah, so the position of chi squared becomes sigma squared. The position of sigma squared becomes chi squared. And in step 4, because the test statistic is chi squared, then in step 4, the p-value will be chi squared CDF, which you will see in our calculator. Okay, like before, the degree of freedom will be 1 less than the sample size. And don't forget, if we are doing two-tailed tests, we need to double it. Double whatever the p-value we get here. Okay, now notes. The population that we deal with needs to be strictly normally distributed. Again, the hypothesis, the underlying assumption is not the same with central limit theorem. Central limit theorem, in central limit theorem, you just need one, the underlying distribution need to be normally distributed, or if it is not normally distributed, then the sample size at least 30, right? Okay, now in this section, we are not using central limit theorem. We are not using central limit theorem. So central limit theorem does not apply for the distribution of standard deviations. Okay, so that's why, again, like in what I said last week for our confidence interval for population variance or population standard deviations, that's why I said that a lot of universities don't use that, don't teach that, because it relies heavily on the fact that the population, underlying population, has to be normally distributed. It is not enough to say that the population has to be symmetric, approximately normal or bell shape, not enough. It has to be strictly normally distributed. Okay, but in my test though, I may not say the population needs to be normally distributed. Just know it, because if it is not normally distributed, then we cannot apply this technique. Okay, but when you apply this in real life, keep in mind that you deal with a normally distributed population. Okay, and usually it is something very, very big, very population with very big size. Okay, now the second note is more about the warning. Be very careful with the wording or what is given. Okay, in my experience with my past students, I usually found students get confused when the given is population or the given is standard deviation. Okay, now the thing is, of course, it affects your step two, your hypothesis, but importantly, in your computation, it will affect here. If they give you the population variance, then that's what you use. Let's say population variance is 4, right? Okay, then you use 4 here. Now imagine if standard deviation is 4, then what will you use here? You'll use 16. Okay, because again, this is the place for variance, not for standard deviation. Okay, now with this background, we will start working on some sample problem. I picked problem from our textbook on number 14. We have done with this type of question many times in 8 point, I think 8.4 and 8.5, and we see that again here. Okay, the same informations, I believe. We are going to do hypothesis testing on the variance or standard deviations of the weights of the world's smallest mammal. Let's see, this number 14, the world's smallest mammal is the bumblebee bat, and which is roughly the size of a large bumblebee. Now, listed below are the weights in grams from a sample of these bats. Let's see, what is the sample size? Seems like they don't give us any sample standard deviation or sample mean, so on and so forth. So we need to find them ourselves. Okay, so let's see what is our sample size here? N equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, N equals to 15. Okay, using 5% significance level is 5%, test the claim that these weights come from a population with standard deviation equal to 0.3. Standard deviation equals to 0.3. So that will be the claim later on. The claim later on is, this is just my scratch word, okay? The claim is standard deviation, not variance, The claim is standard deviation equals to 0.30 grams. Which is the standard deviation of weights of bumblebee bats from one region in Thailand. Do these bats appear to have weight with the same standard deviation as bats from that region in Thailand? So the thing is, for me to test this, I need to find out the sample standard deviation first. I need to find this, right? But for me to find this, I need, of course, to find the population variance, right? Now then, before I get population variance, I need to find the sum of x and then the sum of x squared first. Okay, now let's find that first. You can use your calculator. But when I say you can use your calculator, it's like this, Okay, I will go to my calculator. You may want to write that down first, the data down first, and I prepare my calculator here. This is my calculator. Okay, now I think I taught you this before, how to use your calculator to find the sum of x and sum of x squared by entering the data. Okay, and it will be on, you go to, I think you go to stats. Yeah, you go to stats, and then I will go edit, boom. Now in the past, we already used this, the first column, okay, somewhere in the past, I don't remember when. Okay, let me use column 2, L2. Okay, now then you punch in those you punch in those 15 data. Okay, 1.7, enter, and then 1.6, enter, 1.5, enter. So we did this before. I just want to remind you again. Now, in reality, keep in mind that when you are being interviewed or you work in a company applying some statistic analysis, very, very unlikely you will use a calculator. They will give you a computer instead. Now, if you use computer, then you will use Excel. That's a software that you find in almost, if not all computer. Okay, and then you type this data into your spreadsheet. Then either you use my formula, oops, not 2.5, it's 2. Use the formula that I taught you to do that. And there's some summation notation there though. Basically, if you don't know how to use Excel, then you go to YouTube. Okay, you go to YouTube and kind of like type whatever you want to see there. You want to learn. And sorry if I kind of like have a big concern about how you will use your stats later on, because I don't want to teach something that is irrelevant. It's something you cannot use in your real life, you know. Okay, even if you need to gamble, you use this. Okay, now I finished with entering all the data. Now then, what should I do to find the sum of x, the sum of x squared? Okay, I will go to stat again and go to calc, compute, calculate, and we will use one var stats. This one var stats means statistic of one variable. Okay, so I will press enter now, and you will have list L1. I need to change that to L2. Now, where do I go for L2? L2 is here. This is L2. Do you see this L2? Here. Okay, that's the second of number 2. The second of number 2. So I get second 2. Okay. Now then the frequently, you can, I think you can ignore that. But if you cannot ignore that, you put 1. Now, here you go. So you will get actually plenty of numbers here. But what I need you to put in your test is these 2 numbers, the sum of x, the sum of x squared. And using this later on, you will show the computation on how to get that x bar and how to get the sample standard deviation, Sx. Okay?
But Thomas, even we can do this function for the x bar part, we still have to show the regular way of doing it.
Yeah, you still need to show it to me, the x bar, but it's basically sigma x divided by 15, right?
Okay.
In this case, right? Is the sample standard deviations the one takes some time? Okay, you have some steps, but at the end you still can confirm with this.
For
you
sure.
See what I mean? Just to make sure, right? Now, the reason I want you to do it a quote-unquote long way in your test is because I know that later on you, when you work, or if you go to higher level, then again, if you go to higher level, you will not use TI-84. When it comes to multivariable statistical analysis, our calculator can handle 2 variable at most, you know. So at one point this will be useless. Okay. So basically, I think I want to say that TI-84 Plus is designed to help students who wants to take the stats class at our level or AP stats, you know. Okay, it is not designed for people to work on. Like if you go to work, they don't give you TI-84 when you do TI statistical analysis. No, it's only for us. So what I don't want to happen is you learn what you learn in university or college, one thing, but when you go to work life, you do something else. That's kind of strange. Okay, but anyway, so this is a quote unquote a fast way to get sigma sum of x and sum of x squared. Oh, by the way, if your sample size is like more than 200, I don't think you want to use this calculator. Okay, that's why I will never give you that sample size, a data with that large size. In case of large one, then just go ahead using Excel. It's a lot faster. Okay, it's a lot faster. Now, so my sum of x is 25.7 and sum of x squared is 44.97. 25.7. So is sum of x is 25.7. Sum of x squared equals to 44.97. 44.97. So my first step is to find x bar. Actually, I don't need x bar, but I do it anyway. 25.257 over 15. I get 17. Or something like that. Oh yeah, 1.7. 1, 3, 3, 17. Okay, and then s squared will be 15 times 44.97 minus 25.7 squared over 15 times 15 times 44.97 minus 25.7 squared divided by 15 times 14. I get 0.06695 such that the sample standard deviation is square root of that. I get 0.25875. Now check with your calculator if that's the answer I get. That's what I have here on my calculator. Now, when I plug in the data earlier in L2, I didn't tell the calculator, our calculator, if it is a population or sample. That's why, because the calculator does not know if that's sample or population, then it will just give you sample standard deviation and population standard deviation to anticipate either one of them. Okay, but our calculator will not give us mu, because the computation to get mu, the population standard population mean, is the same to computation to have sample mean. Okay, so there's, even though the notation will be different, but population mean, sample mean from the same data will be the same number. Okay, the sample standard deviation and population standard deviation of the given data will be different, depends on that sample or population. Okay, so but I guess we check with that our calculator. Okay, let's come back. Now, once we're done with that, then we can start the hypothesis testing. The hypothesis testing. Step 1, claim. The claim is these weights come from a population with a standard deviation equal to 0.30 grams. These weights come from a population with standard deviation equal to 0.30 grams. And then step 2, hypothesis. Ultimate hypothesis. We are testing the sigma equals to 0.30. Sigma not equals to 0.30. Notice that the claim is with the null hypothesis. And how many tail is this test? Left tail, right tail, two tail.
Two tail.
That's a two tail. Okay, now then we go to test statistic. Chi squared equals to degree of freedom, which is 14 times sample variance, not sample standard deviation. Look at the formula. Look at the formula. Look at the formula. Sample variance, not sample standard deviation. That's what I said earlier. You need to be careful with that sigma squared and sigma. Okay, what we computed earlier and the test is on the standard deviation, right? But when we plug in the numbers in step 3 and step 4, in step 3, we're actually plugging numbers for the variance. Okay, so I will be looking at the standard, the population, the sample variance, 0.06695 times 0.06695. Okay, of course you can use the sample standard deviation. Just remember to square it. But when you square it back, if you square it, you will get the sample variance back. Okay, and then over the claim population variance. Now, just like before, the parameter will come from the second step null hypothesis, the constant of the null hypothesis in step 2. Okay, but don't forget, well, the number we get here is from the population standard deviation, while the number we put here has to be population variance. Okay, so then I have to put 0.30 squared. Okay, if what we have in step 2 null hypothesis is sigma squared already population variance, then I don't need to square that in step 3. It's already sigma squared. Okay, then let's see, and chi squared, oops, squared equals to 14 times 0.06695 divided by 0.3 squared. I get 10.41444. Then what happened with our step 4? Step 4, p-value. Okay, now our graph, the chi-square distribution looks like this. The chi-square distribution looks like this. Okay, then our chi-square, the test statistic is here. Test statistic is here. This is chi-square would be 10.41444. Now, if we have t distribution or c distribution, it is clear this will be a right tail. Okay, but when it comes to chi-square distribution, it is not that clear. It is not that clear. How do we know that this is this chi-square is actually on the left-hand side, Thomas? The way we know is the following: the peak of chi-square, the peak here, it happens at degree of freedom. Okay, it happens at the degree of freedom. Now, actually, I'm not really sure. Is it at the degree of freedom or at the sample size? I'm not sure. Okay, but on either one of them, though. It's on either one of them. Now, that's how I know that the degree of freedom is 14 in this case, right? Okay, that's how I know that this chi-square is actually on the left-hand side of that peak, of that maximum value. Okay, so then the p-value will be, the one-tailed p-value will be this part here. Okay, that's the one-tailed p-value. But at the same time, because this is two-tailed, I will multiply that by 2. Okay? So the p-value is 2 times, because of the two-tailed, 2 times chi-squared CDF. Now, chi-square distribution starts from 0, not from negative infinity. So the left fence will be 0. The right fence will be n.41444, and degree of freedom 14. Now, use your calculator for that. The p-value I get is 2 times, why I get something strange? 2 times 0.26870. That's 0.53740. Oh, the p-value is so big, huh? Yeah, the p-value is so big, right? because the p-value is so big, then in step 5, informal conclusion, what will my informal conclusion be?
Thomas, for every time we want to calculate chi-CDF, do we have to do the instruction like last time over again?
What instruction?
To put in the CDF formula, to put the chi-square CDF.
Chi-square CDF is on your distribution. Yeah, let me show you. Not the inverse chi-square. No, not inverse chi-square. Not inverse chi-square. It's actually second distribution. And you see the chi-square, if you go scroll down. Yeah, we have chi-square CDF, number 7.
Okay, I got it. Thank
Number
you.
8, number 8.
Yeah, thank you.
Okay, so the lower bound is 0, then the upper bound is 10.41444, and then the degree of freedom is 14. And then I multiplied it by 2, right? That's how I get that. Okay, so not inverse chi-square. Inverse chi-square is the one we actually programmed last week.
Will that be on the exam by any chance?
Repeat it again.
Will the inverse part be on the exam?
You will use that for the confidence interval, right? For confidence interval, if we need to construct confidence interval for population variance or population standard deviation, then the critical value, we use that inverse chi-square. Okay?
Yeah, for sure. Thank you.
And then come back here. What is the informal conclusion? And notice that the p-value is greater than, it's actually so much greater than the alpha, right? The significance level. So the conclusion, the informal conclusion will be fail to reject null hypothesis. Okay. And then finally, the conclusion will be at 5% significance level, there is insufficient evidence to reject the claim that I use double negative here. I use double negative. You can also say there is sufficient evidence to support. Okay, but to be honest with you, when it comes to real life, when you are supporting your null hypothesis and the claim, it sounds really strange. I actually said it right. It's very, very rare we want to say support null hypothesis. Okay, if the claim is with the null hypothesis and we are supporting it, for example, right? Okay, if we are supporting it, we cannot say that I support null hypothesis, I support the claim. Okay, it's actually more appropriate to say that it's insufficient evidence to reject. we don't have enough data to say the claim is wrong, okay? To say the claim is not supported. No, we don't have enough data to reject it. Okay, now, it's kind of like this. If the claim with the alternate hypothesis, we try to support it. When the claim is with the null hypothesis, we try to reject that. Okay, let me finish this first, and then I go back more into the philosophy of hypothesis testing. So to reject the claim that these weights come from a population with standard deviation equal to 0.30. Okay, let's go to our scratch paper here to explain to you a bit more about that philosophy of hypothesis testing. Here's what happened. Remember I said before that null hypothesis is also called status quo. And the alternate hypothesis is the challenging. Okay, now, and if you read our book and a lot of other stats textbook, you will see the wording of our conclusion seems to always try kind of like sounds like siding with the alternate hypothesis. Okay, but the idea is actually more as the following. Status quo is whatever the situation or whatever the statistic, oh, I'm sorry, whatever the parameter that we try to challenge. Okay, we try to challenge. So this is our status quo. I think that's our status quo. Now, for us to say that this status quo is not right, or to be more precise, it's not supported, we need to come up with a sample that is significantly different from what the status quo say. Okay, so basically, for us to say that yes, this status quo is not supported, you need to come up with a test statistic that is very, very far from status quo. You need to be very far, either left tail or right tail or two tail, but very far. Simply because your test statistic is different, but not too far different, you are not enough to challenge status quo. Just like when you want to impeach Trump, for example, you need to come up to some crime that he does as a high crime. It's not a regular petty crime. No, okay. It has to be high crime. Okay. Simply because he, for example, lies to his wife, is not a ground to impeach him. Okay. Yeah. I'm not singling Trump out here. I'm talking about other presidents too. Okay. Like Bill Clinton's case, like how many years ago, right? More than 20 years ago, right? You need to come up with high crime. And simply because that person doing a little lying to his wife or being, to be honest with you, unfaithful to his wife, it's not our business. Okay? Yeah, that's my opinion though, but don't get, it doesn't matter. Bill Clinton was our president. Okay? Now, then, so to challenge status quo, you need to come up with an evidence, a data that is significantly different, not simply a little bit different. Okay, now, so if our if our claim is with the alternate hypothesis, okay, so we play devil advocate, right? Okay, status quo is this guy. This is status quo. We play, and we will play devil advocate as if we are supporting. We try to support the challenging claim, the challenging hypothesis. Okay, so if the claim is with the alternate hypothesis, the wording will be there is enough evidence, there's sufficient evidence to support, or insufficient evidence to support. Okay, so if the claim with the alternate hypothesis, you will see the technical wording will be we will try to support. Okay. Now, on the other hand, if the claim is with the status quo, we will try to reject. Okay, so when we are testing what we had just now, the claim happened to be with the status quo, then the wording is more into there is sufficient or insufficient evidence to reject or not to reject the claim. Okay. You will see that when the claim is with the null hypothesis, the words they use is reject. We try to reject status quo. Okay, but if the claim with the alternate hypothesis, we'll try to support the challenging. Okay, we'll try to support. So the wording will be there is sufficient evidence or not sufficient evidence to support the claim, blah, 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 blah. Okay, now, but this is quite technical though. I will not use that against you. I will not use that against you. So if you go back here and instead you say there is sufficient evidence to support the claim, blah, 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 I will just take it. Okay, I will just take it, yeah. Or you say the sample data support the claim, da, 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 da. Okay, even though the wording is supposed to be the sample data does not support the rejection of the claim. That's actually a more appropriate technical conclusion. Okay, now I know if you take this class with other instructor, I know very, very well some instructors at West LA College, as I know, and also some at East LA College, also at Santa Monica College, are very strict with the way they do conclusion. The wording has to be like this, the wording has to be like that. And of course, they can teach whatever they want with their own class. In my class, I don't mind you to be I'm not really strict with that conclusion. In reality, they don't get that strict either. Okay. Now, why I say that I don't need you to be that strict. Take a look at how I do things. What I want you to be strict is the way they do it in real life. You need to write that step 1, 2, 3, 4, 5. Okay. I know some teachers in university level, they don't do that. I know some statisticians, they don't really stick with this, but I get to the strictest part. Okay. Now then, when it comes to the conclusion, however, it depends on how mature you are in this statistic, right? Okay. Now, what I don't want to happen is I become so picky with my conclusion, but I don't get picky with the structure. More important for me is the structure. You need to know how to get this 1, 2, 3, 4, 5, 6. Okay, the wording of the conclusion, it depends on how mature you are. That's why what I show you here is not what I showed you last week. Okay, why? Because I need you to get used to the structure first. Okay, the 1, 2, 3, 4, 5, 6. How to do this, how to do that. Okay, now then, the wording for your step 6 is the detail, has more detail in there. Okay, yeah. If you give me 2 more weeks, which is not the case, we have only 1 week left next week, right? Okay, but if you give me 2 more weeks, then there's a chance that I will say, oh, your conclusion has to be word has to be worded that way. But it's learning process. That's not something I teach you at once. Even to teach you these 6 steps took me 1 day. I hope you remember that. It took me like 4 hours to build this structure, right? Okay, so because it take me 4 hours to build this structure 1, 2, 3, 4, 5, 6, then I will not focus too much on that how you work your step 6 more than how you do your structure. Okay, so focus on the structure. In this example, I already shown you, in this example number 14, I already shown you how to apply the modification, what we have up here, step 1, 2, 3, 4. And you'll notice I still use the same, I still use that structure though. The claim, hypothesis, test statistic, p-value, informal conclusion, and conclusion. Okay. Together in between, I teach you how to get the how to deal with the p-value if we have two-tailed tests. At the same time, I teach you that, okay? And the little detail on the more proper technical wording for your conclusion. Okay, now let me ask you to do one problem. Let me ask you to do one problem. I will pick this from our textbook, but I know some of you don't have your textbook available now. In a second. The one that I want you to do is number 18. If you have your textbook with you, you can start working on number 18. But I know some of you don't. Let me paste that here. One second. Okay, this number 18. Let me ask you to do the listed values are waiting times in minutes of customers at Jefferson Valley Bank. Now, by the way, the reason I choose this problem is actually to let you know that when it comes to waiting line, it's actually better to do single waiting line. So, for example, you have cashiers here. You have cashier, 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 cashier. If you go to Ralph, for example, you have each cashier has one line to a waiting line, one waiting line, one waiting line, one waiting line, right? Okay, but strangely, if you go to outlets, for example, they usually have only, they may have more than one cashiers, but they have only one single line. The single line is actually more effective though. The single line is actually faster. The line may be longer, but it runs faster compared to if you have multiple cashiers with multiple lines, because you may be standing here and the person in front of you happens to forget this or happen to forget that. Then you need to move to another line, right? Okay. And the worst part is you move to another line just to find out that somebody else in front of you does the same thing. Okay. Well, anyway, something we can do with this question here. So they have waiting times, and the customer gets into single waiting line that fits 3 teller windows. Test the claim that the standard deviation of waiting times is less than 1.9 minutes, which is the standard deviation of waiting times at the same bank with separate waiting lines. So if you have multiple waiting lines, the standard deviation of waiting times is 1.9. The thing is, what if we make it single line? Now use significance level 5%. Does the use of single line appear to reduce the variation among waiting times? This is a numbers. You can use your calculator. Let me give you 4 or 5 more minutes from now. You still have 2 or 3 minutes to do that. Don't worry. I'm not rushing you, but I will start working on this also. Okay, do you get the same result? Anybody can confirm me? Okay, nobody say anything. Okay, fine. So your suggested homework from here, 8.6 will be from suggested homework from 8.6 will be number 5, number 7, number 9 is too long. Number 11, I think number 13 is reasonable. Number 17 is also reasonable. Okay. That's for 8.6. You know what? I would like to say one more thing about this waiting times, the single line uh, waiting lines thing. I said earlier that the standard deviation of multiple waiting lines is longer compared to standard deviation of waiting times for single line. So you have, assume you still have 3 tellers or 3 cashiers, and you have single line or multiple lines. Okay, and of course, the question is which is more effective. And I said earlier, the standard deviation, you will see not only the standard deviation, the average waiting line, the average waiting times for multiple cashiers with single line. Okay, the waiting times here. So this is for single line. This is for multiple line. Now, the average waiting times is actually less uh, if you have single line. Okay, so Thomas, what is the reason that Ralph, for example, if you go to Ralph, or if you go to CVS, let's say, I think some CVS still doing that, or Walmart, actually Walmart is very clear, they use multiple line. They use multiple lines. So Thomas, they basically not using science. No, no, no. They are actually using science. Okay, they are using science. It depends on what is the purpose of them, though. Of course, if I were the supervisor for the cashiers, for example, I want my customers to get through the cashiers as soon as possible. But if you look at the bigger picture, right? When you look at the bigger picture, if you're in a bank, you want the customer to get out of there as soon as possible. Okay, I mean, they want to serve the customer as fast as possible. Okay, but if you are in grocery store, is it what you want them to do? That you set them kind of like finish their shopping as soon as possible? No, right? What they expect is when the longer you wait in the waiting lines, then at the same time, your eyes will go around and suddenly come up, oh, you know what? I still need to buy this. Oh, I need to buy this. Oh, I need to buy this. And hopefully that way they generate more sales, right? Okay, that's why when you go to grocery stores, Ralph is the one closest to my place. They actually put some small things here, like some batteries and a small energy drink, some soda or some candies, right? Okay, and so what is the purpose? While you're waiting, you get attracted to buy 1 or 2 more little things, which, believe it or not, if you look at the price there, the price is actually tend to be on the slightly more expensive side compared to if you buy it other place. Okay, why? Because they try to get into your what do you call that, uh, impulsive buying. Okay, So they are actually doing science. They are playing with your psychology for their purpose, not for your purpose though. Don't forget what they are there for, okay? They are there to make money from you, okay? But not in a way that it's kind of like deceiving you. No, let's just play with your psychology, right? Okay, so I'm not saying that they are not using science. They are actually using science and statistics for their benefit, okay? The purpose of you go to the store and the purpose you go to the bank are different. Everybody agree, when you go to the bank, you yourself as the customer, you want to go in fast, go in and get out fast, right? And the bank also want you to go in and get out fast. Grocery store, no. The longer you stay there, the more you buy. I bet my finger on that. Okay? Well, anyway, so I hope you don't use what I teach you here and then you later on you go to Ralph and tell them to go single line. No, no need, because they are not there for you. They are there for them. Okay? Yeah. Now that's for this 8.6. Let's go to chapter 9. Chapter 9, oops, let me go. Chapter 9. In chapter 9, we get into a more realistic model on hypothesis testing. If in chapter 8, we are testing, in chapter 8, we are testing one parameter, and you will see that's actually one parameter against a constant. So you see in your step 2, always you have a parameter, let's say the mu, the p, or sigma square against constant on the other side. Okay, in chapter 9, we will test two parameters. Testing two parameters. Okay, so we are comparing the sample mean, for example, from two different populations. The population mean from two different populations. And of course, we don't get the population, we use the samples, right? So in our step 2 later on, in this chapter 9, we will be comparing the population proportions or population means or population's variance or population standard deviations. Okay, the sign in between will be, in the null hypothesis, will be either equal sign, less than equal to, or greater equal to. Oh, by the way, I think I need to clarify one thing. I will not, this is in the book, but I will not teach you this part. No, I will not teach you this part. Okay? Okay, I will not teach you that part. The one that I will not teach you is this part. However, you will see when we are comparing two population proportion, population mean, we are dealing with this. Okay, that's our step 2. Okay. Now the thing is, remember in our step 2, chapter 8, we are comparing that with the constant, and that's the constant we will use in step 3. Right? That's the constant we'll use in step 3. Now then, what constant we will use if we have comparing two parameters here? Now you will see later on that we need to modify this hypothesis into P1 minus P2 or mu1 minus mu2, and the other side becomes 0. Now, that's the constant we will use in our step 3 later on. Okay? Now, let's see 9.3. 9.3, we will do hypothesis testing on two population means. So let's say we want to find the population. Is there any difference, or is the income of households in zip code 91754 is less than the income of households in zip codes 91755, for example. Okay, so we have two populations. One zip code 91754 and another population zip code 91755. Okay, that's just zip code. Okay, and then from there, I want to see if the household income here is less than the household income here. But then I get the sample then, okay, and from that sample, I get the sample size for each population and the sample mean for each population. Okay, now of course, to make the model more realistic, we will not assume to have the population variance for each. We will assume we have sample standard deviation for each. Okay, now let's say that's the storyline. Okay, let's say that's the storyline. Now then, in our hypothesis, in our step two, we are comparing mu1 and mu2, right? Like what I said before, we need to get a constant. So to get that constant, I do this modification. I basically subtract both sides by mu2. You can also subtract by mu1. So instead of moving mu2 to the left-hand side, you can also move mu1 to the right-hand side. Either one. But it's a custom that we do mu1 minus mu2. Okay? That way we get the constant on the other side. Now, how about step 3? Now, our step 3 is actually coming from the modification of this. This is what we have in our step, I'm sorry, it should be step 3. In our step 3, when we are testing mu in single variable, single parameter, one parameter, this is the formula, right? What was that? That was from 8.4, I think, or 8.5. 8.5, from 8.5. That's the formula. Notice that I modified this to be this guy here becomes x bar 1 minus x bar 2. Okay, and my mu here becomes mu1 minus mu2. Okay, now then what we had here before, this sample standard deviation, this originally, this guy here is supposed to be originally s squared over n, which is basically that's the standard error, right? That's the standard error. Now then, notice that I basically modified that to be, under the square root here, modified that to be the sum. Okay. Now, the reason of this formula in step 3, besides it mimics what we had before, it actually coming from coming from central limit theorem. Okay, central limit theorem, if you would like to know, it says the following. The other version of central limit theorem. The central limit theorem says the following: if x is normally distributed with mean mu and variance sigma squared, then X bar will be normally distributed with mean mu and variance sigma squared over n. Okay. Now the thing is, how do they get this conclusion? Somewhere in between, we actually have this. Let's say we have x1 and x2. Let me write it down. Let's say I have x1 is normally distributed with mean mu1 and variance sigma 1 squared, and x2 is normally distributed with mean mu2 sigma 2 squared. Then x1 plus x2, when you add them or if you subtract them, it will still be normally distributed with mean mu1 plus mu2, or if you subtract, that's a subtraction. But the variance part will be sigma 1 squared over n1 plus sigma 2 squared over n2. And it is still plus even if you were subtracting them. Okay? That's the statistical foundation behind it. Now, so what happens if you are finding the difference of two mu's? The standard error will be the square root of this. That's the standard error. Okay, the standard error will be the square root of that. But Thomas, if I don't have sigma 1 and sigma 2, what do I do? Then replace it with S1 and S2. Okay, that's how then we get this formula here. Okay, now Thomas, what if I don't understand the statistical foundation? Now, don't worry about it. As long as you know how to use this formula. Okay, as long as you know how to use that formula. Okay. Some notes on step 2 that I said earlier, or step 3 that I said earlier. It's actually modification from what we have in chapter 8. And what if this instead we have sigma 1, sigma 2? Just like before, if you know the population standard deviation, you will go back to standard normal distribution. Okay, if we don't know population standard deviation, then we use sample standard deviation, and our test statistic will become a t distribution. Okay, now let me give you more chance to copy down the formula while I set up the problems for us to work on. Now, I said earlier that the problems you will see here is actually tend to be more realistic, because we are not comparing to what we already preset. We are actually comparing two populations. What do you mean, Thomas? Well, let's say the following. Let's say, for example, how our government actually, and I prefer to say our residents of Monterey Park performing in anticipating and in dealing with this COVID-19. Yeah, so suppose we say, oh, you know what, we are doing well. How do you know that you are doing well? You must compare that with other population, right? You need to compare that with something else. Is it right? You need to compare that with something else. You cannot just say, well, we are doing good or we are not doing good without comparing to anybody else. No. Last night I saw that the number of positive cases we have in Monterey Park, hold on, I think it's 124. And last week we have 117. Okay, so in the last 1 week, we have 7 people extra, right? Now, I'm not saying that there are 124 people roaming around testing positive. No, 120 people, 124 people tested positive, but most of them already recovered. Okay, already recovered. So I'm not saying that there are 124 cases currently. I'm saying there are 124 cases up to now. Okay, cumulative, not at this time, not at this moment, not just at the most. At this moment, I think we have only 4. We have only 7 in the last 1 week. Okay, so if you go to hospital, any hospital in Monterey Park, for example, you will not see 124 people having COVID. No, no, because most of them already recovered, and I don't think we have anybody pass away in Monterey Park. I'm not sure though. I don't look at that one. I didn't pay attention to that one. Well, anyway, how do we know that we are doing well or not? So we're supposed to compare with other city with our size, right? Okay, and how do we know that, for example, LA as a county is actually doing very bad is doing very bad. For us to say very bad, we need to compare that with other county with the same size, right? Uh, of course, if you compare to New York City, yes, New York City is a lot worse. But simply because somebody worse than you doesn't mean you are not bad. No, you are better than them, maybe. Okay, but if you compare to San Diego County, for example, or actually, in my opinion, if you compare to San Francisco, I think we are still a lot worse. Seattle, for example, right? Okay. So if we say we are doing good or bad without do comparison, that's actually kind of doesn't make sense. Doesn't really make sense for general audience. Of course, if we are the one already working with epidemiology, we may know this is good or this is bad. But to explain it to our residents, to people in general, hey, you know what, we can do better, like that, then we need to have something to compare to, right? Okay. So then, uh, let me see. I need to get the data. See. Be patient with me. Be patient with yourself too. Okay. This is the question. I take it from number 10 in our text. Hypothesis test on effects of cocaine on children. By the way, the information given to us always in paragraph like this. What you need to do is to dissect and group the data, organize the data to be relevant to our use later on. Okay, so children were tested, so assess the effect that occur when children are exposed to cocaine before birth. Children were tested at age 4 for object assembly skill, which was described as blah, 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 blah. Now, 190 children born to cocaine users. So I have the first group, group 1, cocaine users. To cocaine users, I assume cocaine users' mom, okay, the mother of the cocaine users here refers to the mom who were pregnant with these kids, has the mean. Oh, okay, so Thomas, why do you single out mom? Because they are the one getting pregnant. Okay, they are the one getting pregnant. Do I place the blame on them, on the moms? No, I'm not. In fact, I want you to realize that. I want you to realize that when your mom when your mom has you in her belly, you know, she needs to take care of you for 9 months approximately, right? Your dad didn't need to, right? You see what I mean? That's why then I personally actually if I compare, of course, I will say that I love my mom more than my dad. Okay, sounds really strange though. It's personal. Okay, it's personal. Yeah. Okay. Mom actually went through a lot more to have us coming to survive. Okay. Yeah. I'm not saying that. I'm not saying that I know I don't respect. I don't love my dad. No. Compare my mom and my dad. Yeah. Of course, it's my mom. Compare you and my dad. Don't even think about it. Okay. Okay. Now, cocaine users. We have 190 children born to these cocaine users. The sample mean is 7.3 and sample standard deviation from this is 3.0. Now, 186 children not exposed to cocaine. So these children born to non-cocaine user, the sample size is 186 and then the sample mean is 8.2 and standard deviation 3.0. Okay, use 0.5 significance level. So that's my alpha, 5%. Test the claim that prenatal cocaine exposure is associated with lower scores of 4-year-old children on the test of object assembly. So I think it has something to do with the visual and motoric development of the children at 4-year-old. Okay. So let me do the claim. Step 1, the claim. Prenatal cocaine exposure is associated with lower scores of 4-year-old children on the test of object assembly. Step 2, hypothesis. Now, in my data, when I organize the data, my group 1 associated to cocaine users, and my group 2 is the non-cocaine users. Let me call this group 1. I already actually used that notation here, N1 and 2, N1 and N2. Okay, so I want the hypothesis is that the assembly assembly test score for group 1 is less than the assembly test score for group 2. Okay, so the claim is here. This is the claim here, right? Now I need to modify this though, because I don't have constant on the other side. I modify this hypothesis to be mu1 minus mu2 is greater or equal to 0. Mu1 minus mu2 is less than 0. Then in my step 3 test statistic, because I don't have the population standard deviation, I use t-score. That will be x1 bar minus x2 bar, 7.3 minus 8.2 minus, what is mu1 minus mu2? Mu1 minus mu2 is 0. Okay, you still need to write that though. Okay, over the square root of sample variance of the first one, 3.0. Let me just use 3 only, over 190 plus 3.0 over 189. Okay, now at the same time I will teach you how to use your calculator. Okay, so let's go to our calculator. How do I punch those numbers in? Parentheses. For the numerator, I will get 7.3 minus 8.2, close parentheses. That's for the numerator. For the denominator, then I divide by parentheses again, just in case, and then square root. And then what is this here? 3 squared over 190 plus, see, division and addition is stronger, right? So when I write it this way, my calculator will automatically do the division first and add, and then add. Okay, 3 squared over 186 is equal to 186. Then close parentheses. And negative 2.90844. That's negative 2.90844. Now then, go to step 4. Step 4, That's left tail of the t distribution. That's negative 2.90844. Is it? Okay. And it's only one tail because it's a left tail, right? It's a left. So the p-value will be ECDF negative E99, comma, negative 2.90844, comma, the degree of freedom. We will use the smaller degree of freedom, 185. Now this 185 here is the smaller of two degree of freedoms, 189 and 186, 85. Now, how do you get this 189, 185, Thomas? It comes from 190 minus 1, that's the degree of freedom for the first group, and 186 minus 1, that's the degree of freedom for the second group. Okay? Now, there's actually a lot more complicated way to compute this degree of freedom here. Very, very complicated, very, very complicated. So it's so complicated such that we then prefer to use this method here, okay? And the result almost always is quite accurate. At least we come up to the same conclusion, okay? And the conclusion will be, I wonder what's that? I'll use my calculator here. So I will get to TCDF the lower is that. The upper, I will just use the answer. And then degree of freedom, 185. .00204. The p-value is 0.0020. And then informal conclusion. The p-value is so small, right? It's very, very small, so we will reject null hypothesis. Okay, so part 6. Conclusion. At 5% significance level. Actually, if you think about this, you will still reject null hypothesis even if the significance level is at 0.5. This is 5%, right? Which is the custom. But even at 0.5% significance level, 0.5%, you still reject null hypothesis. So we get a very, very significant difference. We get a very, very significant difference. Okay. So children associated to prenatal cocaine exposures associated to this lower score of 4-year-old children is very, very significantly different from those without prenatal exposure. Okay, prenatal exposure is associated. What am I doing? I need to say that thing first. There is sufficient evidence to support the claim that cocaine exposure is associated with those of 4 years old children on the test of object assembly. Okay. That's for this one example here. I'm about to give you a break together with, of course, like usual, together with working on a problem. Let's do number 16. Let's do number 16. If you have your book, you can start working on that. Question number 16 use information from number 15 also. So when I screenshot that here, you will see I used information from number 15. So hypothesis test for bipolar depression treatment. Refer to sample data in exercise 15, that's right above that. Use 5% significant level to test the claim that the treatment group and placebo group come from populations with the same need. So basically, to test if a medicine is good, you cannot just say, you know what, I use this medicine and this is the recovery rate and claim that it is good enough. No, you need to compare that to placebo. You need to compare that to a group that they are given a fake sugarly or basically non-effective medicine, something that we know that will not change the result. Okay, now you remember the case of our president once mentioned that hydrochloroquine for the COVID medicine. Okay, and a lot of our media actually says there's not evidence. Okay? Actually, even in medical field, they say there's no evidence. Now, the reason is there are some doctors actually trying this medicine on people. Tried this malaria drug on people, and the result is good. Okay, and then their research was criticized for not having control group. So in a sense that they only use this medicine, okay, but they don't compare that to another group that don't use this medicine. Okay. Now, once they do the control group, they found out that the recovery rate for those without that malaria drug is actually worse compared to if they are given quote-unquote standard treatment. The standard treatment is not using, in the sense that not using this. Okay, so these doctors who use this chloroquine was actually being criticized. Now the thing is though, I want to mention this thing. Okay, if you ask me myself, okay, don't do this to yourself. Don't do this to yourself, and always consult with your doctor. Okay, if you ever get this coronavirus, this COVID-19, if you ever get this, okay, hopefully not. I pray so hard that none of my students get this. Okay, but if you ever get this, okay, then if I ever get this, then I may ask my doctor if this is appropriate for me. Okay, now why I say so? Okay, even though the result from the statistic comers say it's not being supported, here's the thing: these people are the actual doctors. They are not researchers. Okay, so last month, or I should say 2 months ago, okay, 2 months ago, they don't have anything in mind, not even standard treatment. So the only thing they know is people who are prescribed this malaria drug turns out to be more, they actually don't really get this virus. Okay, so they prescribe this malaria drug anyway, malaria medicine anyway. Okay, and they come up with the good results compared to what they have at that time of those people who don't get any treatment. Okay, so then once the dust settled down a little bit, then researcher was the one criticizing them. Now the thing is, these researchers are people like me. They are statisticians. Okay, they're statisticians. They have more time, less urgency to take care of people who cannot breathe. Okay, so they can actually have time to do comparison this and that. Okay, but I think it's actually not really, I cannot accept that this researcher criticized these doctors for using that drug at that time. 2 months ago, so we know so less about this virus. Okay, they did their best. Okay, blaming them right now is trying to judge people who don't know anything 2 months ago for using what we know right now. That's not fair. Okay, now of course I'm not saying that right now just go on still use that. No. Even the researcher right now, if you take a look on how they do the control group, there's still actually some problem there. I personally have some issue with the way they select who are the people using this uh, chloroquine, hydrochloroquine, and who are the people not using them. Okay, if we, let me say what's my issue. My issue is this hydrochloroquine, the way it works is to prevent or to block virus replication. Okay, so it works. It turns out it works pretty well at the beginning of at the onset, at the beginning of the symptoms. Okay. Now, of course, you say, well, some people have that at the beginning of the symptoms, and they turns out to be fine. Yes, yes, I agree with you. Okay, but if you try to apply this medicine, this drug, on people who already on ventilator, it's too late. The virus already take over the lung. Even if you are at middle stage, when the virus already start having a high concentration in your body, then this medicine may not be useful anymore. Okay. Again, the purpose is to block virus replication. Okay. Now then, it sounds like I'm defending Trump. Huh? No, no, I have no interest in him. No, no, no. Uh, but what happened in New York? What happened in China? What happened in Indonesia, and also in other countries? As far as I know, even in Italy, is that when somebody start having a very early symptoms of COVID-19, they give hydrochloroquine. Okay. The problem is the symptoms of COVID-19 at very, very early at the beginning of the onset of the symptoms seems to be very close to flu, such that people tend to wait until it gets worse. Once they are tested positive with that virus, then they start looking for medical help. But once you start getting medical help at that time, giving you HCQ, hydrochloroquine, may not be useful anymore. Okay? Now then, even after we say that hydrochloroquine is not effective for COVID-19, believe it or not, India is using that. And a lot of doctors in New York City is still using that. Okay, but they use that for what? For prevention. The fact that Trump said the same thing and people kind of blaming on him is kind of strange, because he's not the only stupid person who's using that, if you call that stupid. Okay, I don't have access to that medicine right now because that's actually by prescription. Okay, right? But if I have that, I may use it myself. Okay, why? Because my friends in Indonesia who are doctors using that. Okay. Now, should you do that though? No, 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 no. Please don't. Please don't. Okay. Always consult with your doctor. I say that I will use that because I consult with doctors. If you don't trust Thomas. Okay. Don't trust Thomas. Remember, I'm a gambler, right? Okay. Remember, I'm a gambler. By the way, it's similar to Trump, right? He has some casino. Okay. So how to say that? The one that I want to emphasize is this. Okay, doctors 2 months ago has no time. They have urgency to take care of patients. They don't have standard treatment yet at the time, so they come up to whatever they can do. They prescribe the hydrochloroquine. Now, once the dust more settled down, then researchers have more time to do what we call these two parametric tests. Okay, so they are comparing those using that and those using placebo. Okay, and in fact, they go even further, called something double blind. double blind. So the researcher don't know who get the placebo, who get this malaria medicine. The patient also don't know if they get the placebo or the actual one. Okay, so only some people who knows who get what, but the person who knows who get what do not know the result later on. Okay, then from there we can get a better result, but that's after the dust settled down. Okay, now that's why then if we go back to this number 16, if we go back to this number 16, we are comparing, we try to see if this medicine here, paroxetine, is effective. Okay, now how do we know that this medicine is effective? Then you need to compare that to something else. Okay, in my case, I believe I told you before that I have depression, so I take Prozac. Is Prozac effective? Then I need to compare that to another groups with people with depression, and you give them placebo and see the result of these two different groups. Okay. If you put me in some environment and I get better, let's say a stressless environment, and I get better, okay. At the same time, you put people with depression, you give them placebo, and you put them in the same environment, and they also get better. Then it's not because of the Prozac that I get better. It's because of the environment, right? Now, if we change the storyline a little bit, okay, put them in stressful environment, okay. People with Prozac gets better and people with placebo also get better. Then it will even confirm more that your Prozac is not effective, right? Because you get Prozac or placebo, you get the same result, right? So what's the point of you get Prozac, right? Okay. Now, the reason I use Prozac is because in the past they do research and they found out that the result is better than placebo, even though it's not perfect. Okay, even though it's not perfect. If I go into your daily life, just ask yourself about the headache medicine. Which headache medicine is effective for you? Aspirin? Your choices are aspirin, Tylenol, that's acetaminophen, and then it's paracetamol here in Indonesia, and not Motrin, ibuprofen. So when we say aspirin is better or Tylenol is better than ibuprofen, in what sense? Like that. Okay. Saying that Tylenol is better means that you need to compare that to placebo. If I just give you some drink and put some sugar on that, will you feel better? Right? If you feel better either way, then you cannot say Tylenol is effective. You just need some rest, right? Okay. Well, anyway, I try to put some perspective into this question here. I will give you 10 minutes for this and then another 10 minutes for your break. So we come back at 11:27. Okay, let's say 11:30. Okay, 11:30 you are done. So it is possible I will come back at 11:25, let's say, and start working on this. Okay? Okay, I have started working on this question here. Take a look compared to yours. Okay, that's for this example. We did 2 examples here. Of course, you can do more later on. Sum and note. Before I give you suggested homework and notes, we can develop, we can construct confidence interval for mu1 minus mu2 from here. Now then, the best point estimate will be mu1 hat minus mu2 hat. That is x1 bar minus x bar. The critical value is t equals to inverse t critical is inverse t. And then the margin of error will be that critical value times the square root of s1 squared over n1 plus s2 squared over n2. And then the third one is confidence interval for mu1 minus mu2. The declaration is given by best point estimate x1 bar, x2 bar, minus margin of error less than mu1 minus mu2 less than x1 bar minus x2 bar, the best point estimate plus margin of error. Okay. I will not ask you to construct. I will not ask you to construct confidence interval for mu1 minus mu2 in my test nor in my final, but I am anticipating a situation when, for example, next semester, I will be teaching stats again. Okay, and I hope you may become a tutor for my students at least, or you can also become the tutor in other places if you like, for ELAC students or Santa Monica students, West LA College students, whatever students. And now I anticipate the situation when your tutors, the students that you tutor, taking class from other teacher or from other teacher who actually going over this. I'm sorry. Okay. Now, that's one. Second, how about calculator? Calculator use. You can actually use, not in my class, not in my class. In my class, you need to show me hypothesis testing as the way I showed you before. But you can use your calculator actually to confirm some information, to confirm your result. Let me go back to my calculator. Okay, now suppose we go over number 16 again, the last problem that we do. We want to do hypothesis testing on two population mean with known with unknown sigma. So we will go to stats, go to test. Okay, now then if you are doing hypothesis testing of one parameter with known sigma, you will use this one for one parameter. Okay, maybe I screenshot that. Give me a second. Let's go back to our notes first. Yeah, like what I said before, some instructors actually using have heavy use of calculator, right? Okay, so I would like you to know this first. This also, at least to help you when you tutor them. Hey, make some money. Why not, right? It's tax-free. Okay, the first one here, that's for hypothesis testing on mu when sigma known. This guy here, you use t-test, is hypothesis testing on mu with sigma unknown. Okay, now this one is hypothesis testing on population proportion. This guy here. Okay, now this guy here, this thing here is confidence interval for mu with sigma known. Give me a second. I want to go further. Okay. So this is the same, number 7. If I continue down, right? Now this guy here is confidence interval for then sigma unknown. Okay, now what we did just now is this one, this guy here. Hypothesis testing on mu1 minus mu2 with sigma unknown. Okay, this is if sigma is known. Hypothesis testing on mu1 minus mu2 with sigma is known. Okay, you will see this guy here is hypothesis testing on P1 minus P2. Something we will see in section 9.2 later. Okay. Now, this is confidence interval for P. What I just said earlier, this guy here is confidence interval for mu1 minus mu2 if sigma is unknown. And this is confidence interval for mu1 minus mu2 if sigma is known. Okay, so I think I covered most of them already. Yeah, okay. So if you want to check our number 16, we will do this guy. This is for number 16. Okay, that's for number 16. Let's take a look. Number 16, it will be not interval, but test. Two sample t-test number 4. Okay, now you have two options to give them the data. That's usually from the list 1, list 2, list 3 that we have here, right? Oops. That we have here. Remember that? This one? Okay, if you give them the data there. Okay. Good. And then two sample t-tests. I will use stats. Okay, I'll use stats. Now then, my x1 is 21.57. My sample standard deviation for the first sample is 3.87. And then the sample size for the first group is 43. Sample mean for the second group is 20.38. Sample standard deviation for the second group is 3.91. And sample size for the second group is 33. What else? What do we want to check? The check was come from the same mean. So what you see here is actually H1, the alternate hypothesis. Okay, which of your hypothesis, alternate hypothesis? Okay, the alternate hypothesis is mu1 not equals to mu2. Is it pull or not? Don't. The answer will be no. Don't pull it. Okay, and then calculate. Boom. Notice that the difference is they use this degree of freedom, which is different from ours. It's different degree of freedom. But notice that the p-value they have is 0.19091, right? Is not too far different from our 0.195, as I remember. Let me see our notes earlier. Yeah, we have 0.19589. Okay, now notice that we still come up with the same conclusion though, right? We still come up with the same conclusion. Okay, their p-value is 0.19 something. Our p-value is 0.19 something. In both cases, it is above 5%. So we still come up to the same conclusion. Now, the reason they get this p-value is because they use different degree of freedom. How do they get this degree of freedom, Thomas? The formula for degree of freedom for two samples is actually very complicated. Okay, it's very, very complicated. It's how to say, it actually depends on the standard deviation they have too. Okay, but to make our computation a lot easier, we just choose a smaller degree of freedom between the first group or the second group. The way they do it seems like they're adding those two degree of freedom minus some numbers. Okay, minus some numbers. Okay, so I will not teach you that complicated method. We'll just leave it like this. Okay. Now let's go back to our notes. Your suggested homework from here will be your suggested homework from here. Let me write it here. Suggested homework from this section is 9.3 will be number 9. I know this seems to be long. That's why I gave it to you as a homework. This is testing. Number 13. And then number 17. Maybe one more. Number 20. Okay, that's for number section 9.3. Now let me go on to section 9.4. In 9.3, we are doing hypothesis testing on two population means, but those two populations are independent from each other. Independent. Which means basically these two groups here, the one cocaine users, children from cocaine users, and children from non-cocaine users, none of them overlap. They are totally two different groups of children. And in our second example, those in the placebo group, the one using a treatment group, no member in the first group is a member in the second group. No member in the second group is a member of the first group. That's why we say that they're independent. Now, in 9.4, we will be doing hypothesis testing on mu1 on two population parameter, two population mean. On two population means, but this will be a dependent case. We usually call that match pair. What is that, Thomas? We usually use this to see the effect of a treatment such that on the same person or the same object, we will get the result before and after treatment. So suppose for example, somebody have, so let's consider this example here to give you some situation, okay? Somebody have high blood pressure, like me. I basically have pretty much all, all possible disease you can get in a person. You know, let's say somebody have high blood pressure, and then you provide a treatment. Okay, now after treatment, you see the high blood, the pressure again, the blood pressure again. Okay, now then suppose, for example, before the treatment, my blood pressure is 140. After the treatment, my blood pressure becomes 120. Now, can we say the treatment is effective? Maybe, but you never conclude the treatment is effective based on one person, right? Okay, so instead of dealing with only one person, you get a lot of people. So Thomas, his brother, his dad, which is actually quite strange. Now, no, don't use Tom. Don't use my brother. Let's say somebody else's. Okay, and then another subject. Okay, another subject, blood pressure before the treatment is 180, after treatment is 150. Somebody else have blood pressure 145, after treatment is increasing, becomes 160 instead, and so on and so forth, right? Now, we say that in this case, even though we are comparing the difference between the blood pressure before and after the treatment, the objects of the I think I should say the subject of the observations actually the same person. So the first data in the first group corresponds to the first data in the second group. It's the same person's blood pressure. Okay, this is the same person's blood pressure. You see what I mean? Okay, so that's why we say that they are not independent, they are dependent. Okay, they are dependent. You can match this. You can match this. You can match this. Okay, so later on, you will get the data from here, from the first group. You will get the data from the first group, and you will get the data from the second group. We will still test the same thing, though. We will still test is mu1, for example, greater than mu2, which is the conclusion we will get if the treatment is actually effective. So you see, this treatment separates before and after treatment. Okay? The prior and post-treatment. This is for blood pressure. You can also say, for example, the treatment for SAT prep, SAT preparation. Okay. Before you take an SAT prep, what is your score? After you take SAT prep, what's your score? Okay. Now, so that's how we see if an SAT prep is effective. Okay. In my opinion, each SAT prep will always be effective. Okay, will always be effective. So because SAT prep make you study, right? So if you compare before you do SAT prep and after you do SAT prep, it will be effective for sure. Okay, but it's actually because they make you study. If you can study on your own, then yeah, your score is supposed to increase too. Okay, yeah, your score is supposed to increase too. But how do we use this then? Before your SAT prep, when you go to an SAT prep, they take a preliminary test, right, to see where you're standing. Let's say your score is 520, okay, and then after 8 weeks with them in the summer, let's say, your score increased to 700. Okay, but of course, you cannot claim, you cannot support a claim by only sample size of one. You grab more students, right? And if possible, don't take from only one SAT prep. You get some SAT prep institutions and get the scores from them. Okay, now that's how you know that SAT prep is actually useful. However, if you want to see which SAT prep is better, SAT prep, let's say ACI, that's the one well known in St. Gabriel Valley, and another SAT prep that's well known in Koreatown is Elite, for example. Okay, now then, the students you get here is different from the students you get there. You cannot pair them. Then you use independent tests. Okay, now we are not doing this thing. We are doing this thing. So we will be dealing with the same student taking the SAT test before the prep and after the prep. Okay, this is the situation when we use this kind of test. Now, let me lasso this to delete it. So what's the modification? The modification will be done in the following way. The data will be paired. The data you have will be paired, x1 and x2. What you need to do first is to find the difference, which we usually define as x1 minus x2. Okay, so you will get later on d1, d2, d3, all the way to dn, the sample size. Remember, it's paired, right? So let's say you have a data here, you have a data here, you subtract, you get d1. Okay, now then, how about the hypothesis in step 2? The hypothesis will be, we are comparing mu1 and mu2, right? But then we modified that to be mu1 minus mu2, right? Compared to 0, which we can go on further. This is only when we have dependent case. Only in dependent case. That we modify that even further, that the null hypothesis, alternate hypothesis will be mu d compared to 0. Basically, this guy later on will be expressed as mu d, the mu of the difference. Okay, now and then in our step 3, our test statistic, we will use t, which is equals to d bar minus mu d, which you know it will be 0, over sd over square root of n. Now this d bar and sd comes from here. Okay, that's the only difference actually in step 2 and step 3. That's the only difference. Some note. This test boils down to testing on mu with sigma unknown. Okay, we do problems right away. Let's say, for example, I pick problems from number 12. So on page 491, number 12. Number 12. Give me a second. If you have the information already, you can start working on that. Here's the question. Researchers, sorry, this should be 13 and 14. Oh no, it's 3 and 4, that's right, okay. Yeah. So, researchers collected data on the numbers of hospital admissions resulting from motor vehicle crashes. And results are given below for Fridays on the 6th of the month and Fridays on the following 13th of the same month. Okay, now we want to see if the claim is that when the 13th day of a month falls on Friday, so Friday the 13th, the number of hospital admissions from motor vehicle crashes are not affected. So is Friday the 13th bad day to drive? Okay, so it comes from some hospitals, not only from one. This is hospital A, hospital B, hospital C, D, E, F, for example. And we will see this as the first group. This will be the second group. Okay. Now then, I just go on with this question here right away. I will find the difference. The differences will be, so for the D, which is x1 minus x2, will be -4, -6, -3, 1, -1, -7. These are the data. Okay, now then the sample size then is equals to 6. The sum of D is, to add them, -20. And the sum of D squared will be 16 plus 36 plus 9 plus 1 plus 1 plus. You can use your calculator actually plug in the numbers. Yeah, but I think it's faster for me to just do it this way. So that's 52, 62, 67 here. Let me check it. 7. Okay, so using these informations, then I get what is D bar. Negative 20 over 6. That will be 10 over 3. Negative 3.33. The variance of the differences will be 6 times 70 minus negative 20 squared over 6 times 5. So 420 minus 400 over 30, that's 0.66667. So the standard deviation of the differences will be the square root of that is 0.8164965. So that will be 50. Okay, so you see this is basically the setup. Okay, that's the setup. Now then, let's see. Test the claim that when the 13th day of a month falls on a Friday, the number of hospital admissions from motor vehicle crashes are not affected. So that's a long claim though. So claim when the 13th day of a month falls on a Friday, the numbers of hospital admission from motor vehicle crashes are not affected. That's the claim. So I will need to show that the hypothesis will be that the null hypothesis mu, that's actually alternate, that's null hypothesis mu1 is equal to mu2, right? That's the claim. Okay, that's the claim. Alternate hypothesis is when they are not the same, of course. But we cannot work on this. We cannot work on this. We need to modify this to be null hypothesis is mu1 minus mu2 equal to 0, mu1 minus mu2 not equals to 0, and modify that even further, that the null hypothesis, the mu of the difference is equals to 0, the mu of the difference not equals to 0. Okay, so even though it's two population parameters, two parameters, okay, but because we can match them, it becomes a single parameter. Okay, and the parameter that we are dealing with is the mean of the differences. Okay, now step 3. Let me do my step 3 here. I need some space. This is my step 3. Give me a second. Let me see. So the test statistic will be T equals to the D bar. Oh, what's my D bar again? Negative 3.3333 minus 0. Right? This 0 here. This 0. This 0. Partition it so that you know that. Okay, over the standard deviation of the differences, that is 0.81650 over square root of 6. Which will be I get negative 9.9999. Do I make any miscomputation? Give me a second. Give me a second. Did I do any miscomputation? Ah, I have miscomputation here. Here. My bad. This one. This one is wrong. This one is wrong. It should be 49. It should be 49 here. So this will then be, I need to plus 42. So 112. 50, 60, yeah, 112. So this becomes 112. That's always 6 times 112 minus 400. This is 672. So that's 272 divided by 30. This should be 9.06667. So the square root of that will be 3.01109. I guess that's the answer. So I need to change this here to 3.00. 3.01109. And then negative 3.3333 divided by that answer multiplied by square root of 6. I get negative 2.7116. 3. Okay. I'm not sure if you are following me. I feel like I'm talking by myself. But yeah, I fixed my computation earlier. And of course, then I fix this now. Step 4, p-value. This is a two-tailed test. This is a two-tailed test. Again, the t equals to negative 2.71163. I will get the area to the left and then double it. Okay, so p-value is 2 times TCDF, negative E99, negative 2.71163. Degree of freedom is 5. That is 2 times TCDF negative E99, comma negative 2 point whatever, comma 5. I get 2 times 0.02110. I get 0.04219. Oh wow, it's slightly less than 5%. Slightly less than 5%. So informal conclusion. Informal conclusion. We reject null hypothesis. And then the conclusion will be at, I think it's 5% significance level. Yeah, 5% significance level. If they don't tell us the significance level, then we still use 5%. At 5% significance level, there is sufficient evidence to reject the claim. That whatever you say in your claim. Okay, let me do some little cheating. I'll copy paste this.
Thomas, in this case, what if the value is going to be larger than 5%? What should the statement, how should we state that?
There is insufficient evidence to reject the claim.
Okay.
Yeah, because the informal conclusion will be failed to reject, right? Yeah, failed to reject. So it will be insufficient evidence in that case. Insufficient evidence to reject the claim.
Okay. But in the informal part, so in the formal part, we still just write reject, right?
The informal?
Yeah, informal part.
Informal part, we still follow that rule that if the p-value is less than the significance level, reject null hypothesis.
Okay.
And then
Okay.
otherwise fail to reject.
Okay.
Fail to reject null hypothesis. Okay, that's for this one. I somehow think one example is good enough, but we don't know. Let's see. I try to find you a short question. You know what? Let me use problems that I gave from my Handout last, is it from last week? Give me a second. I downloaded it last week. Give me a second. I need to look for the text. Let me take questions from my test last semester. I wonder if I have them. Yeah. Okay, let me ask you to work on this. So a coach uses a new technique in training middle distance runners, and the times for 9 different athletes to run 800 meters before and after training are shown below. What you will need to do first is to find the differences. So that your difference will be the data before minus the data after. Let me call that 1 minus x2. So you need to find the differences here, and then find the sum of d squared, and then after that get the d bar and sd squared and standard deviation of the differences. I think that should take you approximately 3 minutes, and then you do the hypothesis testing. Will take you approximately 6 minutes. Let me make sure I see the question. Let me show you the question then. The questions are use calculator. use calculator to find D bar and sample standard deviation. So basically you get the numbers here and then you plug them in. I will not teach you a more sophisticated method. I will just teach you this step. So this is -1, this is 2, this is 3, this is 0, -1, 4, 2, 0, 1. Now then you use your calculator, plug these numbers in. Okay, and then just see what's the D bar, and what you will see there is actually X bar. Okay, and then the sample standard deviations of the difference. But what you will be seeing was actually S sub X. Okay, if I say use calculator feature, it means just get it right away. You don't need to show the work. You still need to show this though. You still need to show this. Okay, now let me use our calculator here. Here's my calculator. This, let me clear this. Let me clear this one and this two. And comma. Clear this one, comma. Yeah, okay, good. And the differences are, let's see. This one, this. Oh shoot. I have hard time to see my data, and I still need to punch my calculator. So it will be -1. Well, you punch it in yourself. I use my other calculator. So it will be -1. By the way, when you plug in -1, you need to use this guy here. You need to use this guy, okay, for the negative. Don't use subtraction sign. Use the negative sign here. Okay. -1, and then 2, and then 3, and then 0, -1, and then 4, then 2, then 0, then how many data there? There's 9 data. Okay. Let me go back to once I use my calculator. Once I use my calculator, I get 6. I get my D, my D to be, D bar to be 1.11111. My sample standard deviation of the differences is 1.76383. By the way, uh, when we say the new training technique is effective, what would you like, by the way? Would you like the time to be longer or shorter?
The lower the better.
The lower the better, okay? So you expect the difference to be positive or negative?
The difference in this case should be positive.
Hmm?
It should be positive, right? If we
If
wanted.
you say positive means mu1 is greater than mu2. If mu d is positive, if mu d is positive, that's the same to say that mu1 is minus mu2 is greater than 0, which means mu1 is greater than mu2. But that's not what we call effective. Oh, hold on, hold on, hold on, hold on, hold on. Yeah, it's smaller time, huh? Mu2 should be less than. So you're right, I'm sorry, you're right. I was about to say that it's wrong. So yes, you want your mu2 speed to be shorter, to be smaller. So mu d is positive, that's right. So yes, you're right, that's what we need. That's what we need. Okay, then let's start the procedure. So claim, the thing is the claim is worded in question. I need to rephrase it into a statement, into a claim. So the claim will be the new training techniques is effective to improve the running speed. The alpha is 10%, which is quite unusual. Let me erase this so that we don't get. And then that pull the hypothesis. Null hypothesis, alternate hypothesis. Mu1 is greater than mu2, such that the alternate hypothesis mu1 minus mu2 is greater than 0, such that mu difference is positive. That's the setup. Now then, test statistic. Maybe I give you a couple minutes to do this, maybe 4 minutes. Okay, continue on step 3, 4 or 5 minutes. Yeah, this is a right tail test. I get 0.047726, which is less than 5%, so I still reject no hypothesis. So 6-step conclusion. At 5% significance level, there is sufficient evidence to support the claim that the new training technique is effective in to improve the range. I hope you get the same conclusion with me. Now, I would like to use our calculator. Let's go to our calculator. Let's see, how do we use our calculator for this? I need you to help me though. Okay, can anybody help me reading the data? The differences that I have earlier. If not, then I will go to testing right away. Okay, we will be testing t-test because I don't put in the data there. I will just use the statistic there. Okay, the mu naught is 0. The x bar is 1.11111, and then standard deviations of the difference 176383. 176383. 1.76383. And then the sample size is 9. We are testing if it's less than mu naught. which is here. Then I'm my bad. Actually, I want that to be greater than 0. Okay. I want that to be greater than 0. So it should be this one. So my test statistic is 1.88982, and my p-value is 0.04773. What did I mean by that? Yeah, 0.04773, 1.88982. Yeah, okay. That's if you want to use your calculator to work on that. How many examples I give you here? Already 2 examples. Now let me close up this section, this lecture here with 9.2. Last half an hour, we do one more section. 9.2, hypothesis testing on tool population proportion. Modification. In our step tool, the null hypothesis, alternate hypothesis will be involving proportion from the first population and proportion from the second population, right? And we will modify that to be, basically to be P1 minus P2 comparing with 0. That's how we get the constant. Now step 3. We will use test statistic C just like before, but then it will be P1 hat minus P2 hat minus 0. That's P1 minus P2, which will be 0. Over, now this one is complicated. This one is complicated. Over P bar Q bar over N1 plus P bar Q bar over N2. What is P bar, Thomas? P bar is equals to x1 plus x2 over n1 plus n2. We call this the pole proportion. We call that the pole proportion. I will explain later on what is pool proportion. Okay, I will explain later on what is pool proportion. The word pool is actually exactly the same meaning with the meaning of the word we use carpool. When you do carpool, you basically put more than one group together in one car, right? Let's say, for example, I will do problems from number 10 on page 464. Here's the situation. For males, n equals to 1068 for that n1. And then x1 will be 332. While females then 1220, and then x2 is 420. I can put a lot of possible stories here though. For example, I do survey, and this is the survey, the result for asking for if the object of the observation is supportive of President Trump in handling this coronavirus pandemic. Or you can say this is the number of people getting osteoporosis, or the number of students who pass statistic class, or the number of people who support that we open the economy, right? Okay. Then we want to see if males is, let's say, the proportion of males, more males supporting opening the economy compared to females, or more males supporting the president in handling the pandemic, or more males having osteoporosis, for example. Okay, that's just now. So you will see from the males, we will have P1 hat, which is the proportion for the males. That's 322 over 1068. What's that? That's 0.31086. While, let me put a line here so that you know that this is the one given. The one below that I need to compute. Okay, P2 hat is 420 divided by 1420. That's 0.3446. Now, what is pool statistic? What is a pool proportion? I'm sorry. Pool proportion, if you put this male and female in the same room, you pull them together, you put them in the same pool. Okay, you put them in the same pool, then how many people we survey in total? The number of people being surveyed in total is 1068 males and 1220 females. Okay, and how many of them actually agree to open the economy? How many of them get osteoporosis? How many of them supporting the president in handling coronavirus? This. Okay, so when you pull them together, we basically get rid of this partition. And you add them, Okay. Okay. Then this will give me, this is 752 over 2,280. And the pool statistic, this is P-bar. The pool proportion will be 7.2 divided by 2288. That's 0.32867. Now we can start the procedure. Okay. Suppose the claim I make up the stories. Okay. Suppose the claim is more female experience osteoporosis than male. So hypothesis. The null hypothesis, alternate hypothesis. More females means the male one, the P1 is less than half. Okay, so P1 is less than P2, that's the claim. And that's a left tail, right? And I subtract by P2. That's what I get. That 3 and statistic. This is the long one. And statistic, because it's on proportion, we will always use Z. On the top, I will get P hat 1 minus P hat 2. Over on the denominator, however, I need to use the pool proportion. Okay. I will need to use the pool proportions. So if that's my P hat, my Q hat will be 1 minus that. 0.6713. 0.32867 times 0.67133 over 1068 plus, but this is all under the same fraction, under the same radical though. Okay, under the same radical. You don't separate the radical. No. It's the radical, the square root of the sum. 0.32867 times 0.67133 over 1220. Now you will see for this section, that's the most painful part. In fact, to set it up is easy. To set it up is easy. This is easy. Okay? This is hard. Okay? Now then, how to compute this? Let's go to my calculator. Compute parentheses 0.310 2.86 minus 0.34426. 0.34426 close parentheses divided by the square root of this one is long. This one is long. 0.32867 times 0.67133 divided by 1068 plus. Notice that I'm still under the square root. Okay, don't close the square root. I'm still under the square root. And then the full proportion again, 0.32867 times 0.67133 over 1,200. Boom. So that's negative 1.69682. That's negative 1.69682. Now, everything after this is the way we did it before. So step 4, the p-value. That's a left tail, right? This is C equals to negative 1.69682. P-value is normal CDF because we use Z. Normal CDF, negative E99, negative 1.69682, comma 0, comma 1. Or you can just ignore that 0, 1. Okay. Let me go back to our calculator. I want to use this result here. So normal CDF, negative E99. The upper is my previous answer, right? And then my mu 0, my sigma 1 is 0.04487. That's 0.04487. And because the alpha is 5%, then we come up to the conclusion that, informal conclusion, let me write it here to save some space, that 5 informal conclusion reject null hypothesis. And then conclusion at 5% significance level, the sample data support the claim that the sample data support the claim that more females experience osteoporosis. Okay. Now, even though the wording sounds like we have more females experience osteoporosis than males, we're supposed to look at the proportion. We are not looking at the number of people experience females. Because what? It is possible you happen to observe more females, you ask more females uh, members in our society, such that then you end up with more females in the experiencing that. Okay, imagine if the number of females you ask is 1,000 something and the number of males you ask only 68. If the number of males you ask is only 68, there will never be that the number of males be more than the number of females experience osteoporosis, right? Okay, so to avoid the bias of having uh, not enough males or not enough females that we observe, then what we do is we look at the proportion instead. Okay. Now I have approximately 7 minutes left. Let me go back to our calculator. If you want to confirm your answer using calculator, okay, but never show this in your test. This is not how I want you to show me the work. You will go to test 1 proportion C test. No, I'm sorry. This is 2 proportion C test. This is 2 proportion C test. It's 2 proportion. We are comparing 2 proportion, and every time you deal with proportion, it's always C test, always C statistic, or if you do confidence interval, it will be 2 proportion C intervals. You never have 1 proportion T interval, never. You never have 2 proportion T interval, never. Okay, we always deal with, when it comes to proportion, it's always C. Okay, so this is 2 proportion C test. Now then, what is my N1? My N1 is 1068. I'm sorry, my X1. Sorry, I look at the wrong one. My X1 is, this is 332. And then my N1 is 1068. My X2 is 420, and then my N2 is 1220. And then I want to test the claim. We look at the alternate hypothesis that P2 is greater, more female, right? Boom. And then copy. Now compare the C-score you get here with the C-score I got earlier. That's my C-score. Compare the C-score I have here and the C-score I get earlier. The C-score I get earlier is negative 1.69682. Okay, and the p-value is 0.04486. I get 0.04487. That's in mine. I wonder why I get that difference. Oh, it must be because I do rounding here. It's because of the rounding error that I have here. Yeah, it's because of the rounding error I have there. Which here, Thomas? Here. I do the rounding that I have here. Okay, the rounding I have there. And actually, I have rounding error also here, right? Okay, But Thomas, with that kind of rounding error, is it possible we get different answer? It's possible, but it's extremely small possibility. Extremely small possibility. Now, that possibility will be higher of getting the different conclusion if you round it to only 2 decimal places. Okay, that's why I want you to round more, 5 decimal places. Okay, and then we get the result from our calculator here. Okay, they even give us the p hat 1 and p hat 2. They compute it for us. Okay, they even give us the p bar. This is the p bar, the p hat here. They don't have notation for p bar, so they use p hat. Okay, that's the 0.32867 that I used earlier. Let's go down, see what they have underneath there. Nothing. That's basically it. Okay, that's for our class today. Suggested homework from this 9.2 will be, this is number 10 from our textbook. And your suggested homework from here will be number 9, number 13. Oh, no, you don't need to do confidence interval. Number 15. Number 17. Number 21. Maybe one more. And number 25. Okay, that's for today. Next week, like usual, I will post your test at, what time did I post your test last week? Last time, I think 8:45, huh? Your test for,
I'm pretty sure it was 8:30 for the last time.
last time is 8:30. Okay, then I still post it at 8:30 then. Okay, 8:30, post it. Okay, but because there will be some writing, a lot of writing, then I give you even more time. Usually I want you to turn it in at 11 o'clock, right? You need to stop at 11 o'clock. I will give you up to 11:30. Okay, now then fully upload it at 11:45. Is it okay? So you basically have 3 hours to work on that. And actually, if you think you need more time, I don't think so. I don't think so. But if you think you need more time, let me know so that I can change the. No. You know what? Let me just do it this way. Let me just do it this way. I changed it even more so that I don't need to change the number twice. So 11:45 you stop, and you have to turn it in by 12 at noon. How about that? Better? So you have effectively 3 hours, I hope, effectively 3 hours to work on the problems. Okay, you have around 3 hours to work on problems, and then the lecture will start at 12 o'clock too, which basically just review. I don't think I will. Yeah, I can do one extra section, but I think I will consider that I need to do linear regression, the simple linear regression. I need to do that, but I will see you next week. you know, depends on how I feel the class going. Okay. Yeah. Then yeah. See you next week then.
Thomas?